All right, welcome back to the Futurism at JHU podcast. I'm here with Ricardo and Max, and today's topic is the quantum realm. So, to get the conversation started, Max, could you give us a basic introduction to quantum computing?
Yeah, sure, absolutely. So just to preface things, I am absolutely no expert on quantum computing at all. It's a field of research that is continually ongoing, and it is so massive, and you could spend the rest of your life um, studying quantum physics and still have so much more to learn. But I'm here to give just a basic introduction on what quantum computing is and what it was invented for initially. Okay, so okay, we're going to compare quantum computing to classical computing. Classical computing is what we do on our computers every day. Okay, so all of our computers are classical computers. Now, a lot of times there's a discrepancy when people think of quantum computing as being just a faster classical computer. That is absolutely not the case. A quantum computer is sort of an entirely different machine from a classical computer. So, for example, a classical computer runs on binary, right? It sort of speaks binary. That's like the fundamental language of a classical computer is ones and zeros, ons and off switches, right? And that's sort of how we're able to, and that's sort of just how a classical computer functions. Whereas quantum computing is slightly different. So the way that we represent these ones and zeros in classical computing, we use bits, right? And a bit is either on or off, represented as a 1 or a 0, right? In quantum computing, we have what are called qubits. A qubit is on and off at the same time, which is sort of hard to understand. I get it. That's just sort of like that's part of the quantum physicsy part of how a quantum computer is built. The state that we call this, the qubit being in the position of 1 and 0 simultaneously, is what we call superposition. So when a qubit is in superposition, it is either 1 or 0. Okay? Now, this is where quantum computing becomes handy. Say that you have 4 bits on a classical computer, and you want to represent some binary digit, right? Let that be, say, for example, 1001. Okay? You could potentially represent 1001 by flicking the first transistor on, the next keeping the second 2 transistors off, and then flicking the third one to the right on, right? That could be the binary digit 1001. And you would be able to represent that instance at one given point, right? Now, the fact that you have four bits and you're using binary, right? There are 16 possible combinations then at that point that you're able to arrange your sort of binary digits in, whether it's 1010, 1110, so on and so forth, right? Now, with qubits, as we said before, qubits are in a state of superposition, meaning that they are simultaneously 1 and 0 at the same time, right? So while a classical computer is able to represent one instance of 16 out of 16 combinations, a classical computer is in fact able to represent all 16 combinations at one time using 4 qubits, which is kind of absolutely crazy, right? That's basically the big difference between classical computing and quantum computing on a, I guess, engineering level, right? Now, when we talk about practical applications of quantum computing, a quantum computer was initially invented so that we could simulate quantum experiments because it's virtually impossible to simulate quantum experiments on a classical computer because there's basically not enough data on a computer and on a classical computer, and the way that a classical computer sort of quote thinks about data is totally different than the way that a quantum computer thinks about data. A quantum computer thinks about data in the way that is related to the quantum realm, which and the fact that it's designed this way allows us to simulate and perform quantum experiments that we can't necessarily do on a computer or in a traditional lab of sorts, which sort of leads us into our next topic, which is just what we can do with quantum advancements and understanding the quantum realm. That would enable us to become an interstellar species due to the fact that we sort of have to understand quantum physics before we're able to, say, create a wormhole and travel across the universe, right? So that sort of leads us into humans becoming an interstellar species. Quantum computing is the very first step to making that happen. So that's where the technology is right now, as far as that goes. I think that's so exciting. I know it's a lot to take in. What do you guys think?
I personally think that it's a super exciting realm, as you've said before. We're exploring all these different possibilities. There are a lot of things happening all around us, and I personally believe that humans are not necessarily a species that was designed to be contained in and of itself in just one planet. Just due to our curiosity and our way of thinking, we want to explore everything. We want to discover everything that is unknown. And of course, if we want to discover the ends of the earth, which we are doing right now, but even the ends of the universe, we're going to need more tools to do that. And definitely the quantum computing and everything in the realm of physics that is going to lead us to that point is being developed right now. So I feel like that's definitely going to be a step forward, leagues into the future. But what I'm really curious about is what you guys think on like how far do you think we will get with quantum computing in maybe like the next 5-10 years? Do you think it'll become or expand so fast that we'll actually be able to realize to some extent the ability to create space travel that is more efficient or takes us further?
I don't know. I think that right now it's I think that the growth is exponential, but we're at the very, 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 very beginning of the curve, right? So I'd say within the next 5 years, we're probably not going to see a whole lot. I think that, from the bits and pieces that I've read, I think that we're sort of on to something. I think I said this yesterday to Nicholas that as far as quantum, our understanding of quantum physics goes, it's kind of like we're in the witch doctor phase of medical science right now. Right? So we're kind of in the stage where we're just sort of curiously trying a lot of new things, right? Like we know that certain things work, like we know that certain herbs might make certain things feel better, right? Like it might cure certain conditions. We're not really sure why or how, right? That's kind of where we are as far as quantum physics goes. We know that certain things react a certain way, right? We're not sure why or how, right? So, like I said, we're kind of in the witch doctor phase of quantum computing and just understanding quantum physics.
Yeah, to pull another quote from Max, he said, "It's the basis to understanding how we get there." So that really stuck with me. But I
Right,
guess
and there
thinking,
being sort of mastery of, I guess, time and space in that
ooh,
sense.
yeah, for sure. So, okay, so let's say theoretically we're able to advance quantum computing, or maybe quantum computing
Leads to a
leads
certain
us
discovery.
exactly leads us
Yeah.
to a certain discovery or different technology that can then lead us to something that can allow us to be an interstellar species or to have extremely advanced space travel that we've never had before. So let's say we're able to do that, right? So we're able to create I don't know, a spaceship. Well, okay. Yeah, like a spaceship or something that can get us to I think you said the nearest star system you said is 4 light years away, right? Alpha
Yes.
Centauri.
So Alpha Centauri, yes, it's roughly 4 light years away is how far, and that's the closest one.
So, if we'd want to get there within a reasonable time frame, we would have to what would you say our speed would need to like how fast of a spaceship would we need to get there? Would you say?
See, that's so tough because mm, the closer. Okay, so this is a sort of a wild thing to try and unpack, but once you start approaching like near light speeds, and now we're talking about light years, right? Once you start approaching near light speeds, what ends up happening is Einstein's theory of relativity starts kicking in, right? So what happens is as you go faster, more time passes on Earth than does for the people in the spaceship. So for example, if you're traveling near the speed of light and you're holding a pocket watch and 1 minute passes, it's possible that a whole year passed back on Earth to the people who aren't traveling that speed, right? So when we start talking about these super far distances and far speeds, it's sort of impractical to start thinking about like getting there going fast, which is why quantum travel is so important and figuring out how to use a wormhole to sort of like bend space. So a cool visual that I saw one time was think about space as a piece of paper, and instead of traveling across the piece of paper, you fold it. And then you just hop from edge to edge, right? And then you unfold it. Then you're on the other side. Does that make sense?
Wait, but
that would be theoretically the fastest way to get there, which would be like the equivalent of quantum travel.
so
If you were to think of space as a piece of paper that you're bending.
yeah, that's what I was gonna ask because space is 3D or well, it's expanding
Yes.
in all directions, right?
Yes.
So how would you yeah, I mean I would get it if it was flat, like flat earth theory, right? You just
Right.
fold it into a tortilla and you can put China and the US together or something. But like how would that work with a 3D object? Like are you opening like with the idea of wormholes, are you opening like you're opening a hole in space and time and just popping out the other end? Like so that could like teleport us to that next star system somehow?
Yeah, great question. So in the film Interstellar, it's explained sort of the same way, like sort of expanding on that. When you fold the piece of paper, imagine that you fold the piece of paper in half. Imagine that's your space, and you punch a hole through that piece of paper. That's you traveling to the other side of the piece of paper, right? And now you're there, right? What's a hole? What is a circle in 3 dimensions? It's a sphere, right?
Yeah.
So a wormhole would have to be spherical.
Oh.
Right? And it's sort of like, and that's essentially what is happening is you're taking that 3D space and you're compressing the space in that sense. In the same way that you're sort of folding that piece of paper, you're bending the space.
My mind has left the chat. I'm just letting right? Brain cells have left the chat.
And so that's why like simulating quantum experiments is so important in quantum computing, because it'll lead to another technology, which will lead to another technology, which will lead to another technology, which will eventually lead to us having mastery over space and time in that way, which can then lead to us becoming an interstellar species and visiting planets that we've never dreamed of visiting.
Yeah, for sure. So, okay. So, I guess I'm going, okay, this is kind of changing gears, but like going to like Ant-Man, right? Like the movie Ant-Man.
Right, yeah.
Where they can basically shrink themselves and then he gets down to the quantum, like he's literally physically in the quantum level, I think.
Quantum realm, yeah.
The quantum realm.
Right, yeah.
And then through that, this is like the whole Marvel movies, synopsis,
right,
I guess, but they're able to travel through time. So do you do you think it'd be possible to shrink someone down to such a tiny level and potentially travel through time somehow? Like, because we're in the quantum realm and we're in a whole different, like, it works in a whole different way from what we normally think of.
I think I don't know. This is just my imagination going wild. But so have you guys heard of like, you know, black holes are a thing?
Yeah.
But we don't know if like white holes are a thing. Where like if
White
something
holes?
goes in,
right.
something goes out.
Well,
Ooh.
okay, yeah, because the idea of like a black hole existing means that there has to be like an opposite, right? Because it's
Yeah.
sort of a deficit in the universe. There has to be an opposite that counters it. It's the idea of like there being matter and antimatter,
Yeah. And they cancel each other out essentially.
right?
And so what I'm thinking is essentially with that same regard to like being able to travel if through space and time if you like compress yourself to a certain degree, well, you know, that's essentially what a black hole does, right? It compresses matter to the tiniest it can go.
Yeah.
So assuming that Marvel has something right going in its script writing, right? For like Ant-Man, we could assume that potentially everything that is eaten by a black hole is potentially in or traveling through the quantum realm,
Because it's literally
compressing
been
it to
compressed.
such a small degree that it's reaching that level of like pure space and time.
Wow, that's intense. I never really
Dang.
thought about it that way.
I mean, of course, we're giving some credit to Marvel, at least in their screenwriting and their physics,
Right,
which
yeah.
might not entirely be correct, but it's just a thought.
Jeez. So the key is, can we survive a black hole?
Yeah.
Oh my
Or like
gosh.
It
how
sounds
like
very painful.
yeah, and that's kind of like the weird thing about like black holes and stuff is that we know what they are essentially, but we don't really know their specifics. We don't know how a person or a living creature would react to being eaten by a black hole, right? What would they experience?
Right.
So it's this whole thing because even if you send, let's say, like a machine or something, will it be crushed? Will it just disappear on you? Would you be able to track what happened to it at all?
Okay, interesting thing about this. I was talking to Nicholas the other day about this, but the same thing that I was saying about time and speed is the same. The same thing goes for gravity, right?
Right.
So remember how I was saying the faster you travel, like if you're traveling, like as far as when we talk about near light speeds, right? Like if you're like if you have a stopwatch and 1 minute passes in your very fast moving spaceship, it could be a year back on Earth. It's the same thing for extreme gravity as well. So if you're chilling around a black hole,
Right.
and this, like it feels like this whole conversation actually is revolving around the film Interstellar. So if this interests anybody,
Watch Interstellar.
Totally watch
Yes.
Interstellar.
And Ant-Man.
Right, yeah. But if you're chilling around a black hole, like fairly close to one, and you have a stopwatch, it can actually, like, minutes can actually equate to days, and like if, well, I won't give that away in the movie, but like minutes can equate to days, and the closer that you get to the black hole, the more you're impacted by its gravity,
Right.
the more the time slippage is. So theoretically,
Wait, time slippage.
right? Yeah.
Explain.
So it's sort of just, when I say time slippage, I'm referring to the ratio of time that a person near the black hole is experiencing versus the time that somebody back on Earth is experiencing.
Oh,
So
okay.
for every 1 second that somebody is near a black hole, it could equate to 5 seconds, 10 seconds, a minute back on Earth.
So you're saying the closer and closer you get, the bigger the rate, so the bigger the time slippage is. Is that what you're...
Sort of, yes. It's more, I wouldn't necessarily relate it to distance. I would relate it more to, I would relate it closer to gravity, that, like being within a gravitational field, right? So it's, because you could be very far away from a very strong black hole, right?
Yeah.
You could be very close to a planet, and a planet has very minimal time slippage, right? It has some, but not, compared to like, not having any gravity acted on you, but it's totally minimal.
Gotcha.
I just wanted to ask something, and this just popped in my head.
You're all good.
But So you know how gravity is a thing, right? It's there. We know it exists.
No, please explain further,
Uh,
Ricardo.
okay. So
Gravity.
essentially, gravity exists because
Yeah,
there's mass. The more mass something has, the more gravity it has. That's what
Right.
we've all learned throughout our schooling years, up till now.
Right, yeah.
And I'm not saying up till now because I'm about to make this life-changing discovery now. That's not what it is.
Right, yeah.
But okay, so me and my roommate were actually playing this visual novel. And anime story. That's not
Name?
what matters though.
Name?
I think it's called Aokana. It's like a romance, like visual novel thing.
All right, check it out, guys. Check it out.
But the interesting part was in that, like, a main part of the story revolves around gravity shoes or anti-gravity shoes, and essentially, one of the things that they mention is that these shoes they were able to make these shoes because back years ago, scientists discovered a new like atom, I guess you could call it. So think of like light, right? We didn't think of light as being like something physical until people discovered, photons.
Mhm.
So could there potentially be something like a graviton? So an actual,
An actual particle.
particle that causes gravity.
Yo.
And the thing is, if you look at research that has been going on right now, some people believe in it, some people don't believe in it, but there's not enough research to say for sure that it isn't a thing or that it can't be a thing.
Ooh. I've
That's
never
trippy.
heard that. That's so cool.
Yeah, I haven't heard that either. That's really interesting. And especially, like you said, relating it to a photon, because when you start talking about a photon in itself is super trippy because it's like, is it mass? Is it not? Like, right?
Well-
so it's like when you start talking about gravity, which is sort of like very closely related to mass, it's like, right? Like, wow.
I was gonna say from like physics, they say there's like the wave particle duality of light, where it's like it can act as both a wave and an actual like physical particle.
Right, yeah.
So it's almost like when you're talking about like qubits, like it's
Right.
in flux in a way.
Right, yeah.
Like it can be both simultaneously. I think that's kind of how I think of it.
Yeah, that actually, I'm pretty sure that is specifically quantum physics, the fact that it can be both. Yeah, I think that's like, I think that when you talk about that, you are referencing quantum physics.
Okay, so kind of as like a wrapping up question, this is kind of bigger picture. So let's say we're able to, we become an interstellar species. We can travel through time and space. We have wormholes. What are the societal impacts of that? Like, what does society look like once we've branched out from Earth and all of a sudden we have, in a sense, become like, masters of the, I don't want to say masters of the universe, but kind of masters of the universe in a way. Like, what does humanity look like at that point? Like,
And that's a wrapping up question.
that's, yeah,
I'm kidding,
yeah,
I'm kidding.
oops.
No, I think
Little-
that's such an
little big.
I think that's such an interesting thing to think about. When we start, think about how big that we think the Earth is and how many different parts of the world there are and how many different cultures there are on Earth. Suddenly, we'll have quite literally an infinite amount of room for different cultures and different just different everything, right? Like there could be quite literally millions of different languages at some point, right?
Right.
And
Sure.
Specifically, what I wonder is what communication would look like, because right now we have the internet, which connects the whole world, right?
Yeah.
Is there going to be some sort of like universal network? And if so, it would have to be quantum, right?
Yeah.
Because it couldn't be like, based on wires, right? Or like radio waves like our current internet is, right? It'd have to be quantum related. Which is part of, actually, I was reading about how they're actually able to teleport quantum like bits between two particles, which is Ricardo. Do you know about this? You keep nodding your head.
Right.
I've read briefly about it.
Now I just remember that they did it over a long distance, and it was pretty quickly. The thing that I'm not exactly sure, and I probably should have done a little bit more research on it, was actually like the way they were doing it, because apparently they use a fiber optic cable to be able to transport a bit, but I feel like in the way that they were quoting it, the fiber optic cable was used more as like a railway rather than it being the main source of transportation between the 2 points.
Right.
Because then if you think about it, well, fiber optic is technically going at the speed of light. We don't call that transportation, like, teletransporting. So in this case, the cable, at least in my, view of things, would have only been sort of like a railway to be able to pinpoint where something should go to, rather than it being the main form of transportation,
Right,
using light or near light speeds to be able to transport and call it teletransportation.
See, in this experiment that I read about, they were using 2 entangled qubits to transfer information, because the way that entanglement works, on a very basic level, not anything complex, with one particle, if you if you affect one particle that is entangled with another particle, it'll move the other one, right? Like if you do something that affects one particle, the other particle will react. Einstein called this spooky action at a distance.
So scientific.
Right. And so that's one way that we could theoretically, and it happened instantaneously too, right?
Right.
So like this could be sort of the very, 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 very beginning of our quantum internet.
So invisible cables
Yes.
connecting everything together. I mean, that would be
That's string
extremely
theory.
cool.
That's basically string theory. Invisible little strings that connect everything together.
Yeah, because just
Oh.
imagine like being able to. I mean, we already do this over like Wi-Fi, but being able to stream, right, or casting your screen or what you're doing from one screen to another, but in this case, with no Wi-Fi.
Right, yeah. Crazy.
Dang, this is so cool. All right, well, that has been it for this episode of the Futurism at JHU podcast. Thank you, Max and Ricardo, for
Thank you.
literally
Yes.
destroying my brain cells because I have no concept of this stuff. But, neuroscience is more my specialty. But this has been really interesting. We hope you enjoyed it, and we'll see you on the next one.
All right, see ya.
Bye. Bye. Bye.